So is the screen visible now?
Yes, sir. Yes, sir. It is visible.
Yes.
Okay. So let's get started. Now, last time I talked about the Galilean transformation. So we need to review the concept of what you know from your fluid mechanics course as material derivative. This term material derivative is also referred to as substantial derivative or total derivative or derivative following the fluid particle. So this quantity relates to rate of change of flow quantities for a fluid particle. So as a particle moves from one point to another in space, you want to know how the property of the particle changes. So since the identity of the particle remains the same, we call it material derivative. The term material comes from matter. So material derivative means derivative for an infinitesimal piece of matter which remains the same as the particle moves. And this substantial, it comes from substance. It means that the substance is the same. And it is also called total derivative. The reason being, for a given particle, if you look at the x, y, z coordinates, they are functions of time. Okay. So phi x, y, z, t is the Eulerian description for a flow variable such as a velocity component or pressure. Okay. So if this function is known, then you can predict simply by looking at the values of the function, what are the values of the variable at different points and different instances of time. But if you want to find the same quantity for a particle, then you have to substitute the coordinates of the particle into this function x, y, and z. So if you look at the phi for a particle, it will be phi of xt, yt, zt, t. So if you want d phi dt, okay, then you have to use the chain rule. So that is why it's called the total derivative, not a partial derivative. And it's common to use this symbol capital D dt. Now in your first level course, you would have derived this. D phi dt is del phi del t plus v dot grad phi, where v is the fluid velocity. So if you use Cartesian coordinates, then v dot grad phi will have three terms, the sum of three terms. So the x derivative del phi del x is multiplied by the x component of velocity vx. Okay. The y component of the y derivative of phi is multiplied by the y component of velocity, and the z partial derivative is multiplied by vz or the z component. So this x here and this x here, they match, and this y and this y match, and this z and this match. So this symbol capital D phi dt stands for the sum of these four partial derivatives. Of course, these are multiplied by some coefficients. Now, if you don't want to use this symbol, we can simply write small d phi dt. That is also used by many authors. So we need to distinguish between these two derivatives. So by definition, del phi del t is the partial derivative keeping x, y, z fixed. So if you go back and look at this function, it's a function of four arguments, x, y, z, and t. So when you take a partial derivative with respect to one of the variables, the other three have to be kept constant. So when you look at del phi del t, what is kept constant is all the coordinates x, y, z. So that means it tells you what is happening at a given point. So del phi del t, I'll write as, to be more precise, within parenthesis del phi del t, and outside a subscript x, y, z, which means the variables which are kept fixed in this partial derivative. So the definition of this is limit delta t going to 0 of delta phi by delta t, and this delta phi is the change in phi at the same point but at two instants of time. So as you can see, this x, y, z here, this x, this y, this z is the same as this x, this y, and this z. Okay. So what is changing is the time. Now similarly, if I look at the gradient del phi del x, the variables that are kept fixed is y, z, and t, the other three. So here x is incremented, y, z and t are kept the same. And similarly, if you look at the partial derivative with respect to y, then y is incremented and x, z and t are kept fixed. And when you look at del phi del z, z is incremented and x, y, t are kept fixed. So all these partial derivatives with respect to the spatial coordinates are at a given instant of time, and keeping the other two spatial coordinates fixed. So that means at a given instant of time, if you move along a line with constant y and z, say y equal to y naught, z equal to z naught, okay, but x is changing, then the rate at which x changes is del phi del x. So this you can think of as the directional derivative of phi in the direction of x. Now it's cumbersome to keep writing this bracket and the subscripts here, so we'll not use this, but you have to keep, in fact, the definition of this partial derivatives in your mind. So as soon as you see del phi del x, in your mind you should think that y, z and t are kept fixed. Okay. Similarly, if you see del phi del t, in your mind you should know that x, y, z is held fixed. Okay. So these are simple things. Now, to fix your ideas, suppose I want to find del phi del t, then phi is x, phi is y, phi is z, and phi is t. Can you tell me what will be the answer to question number 1a?
0.
Okay. B?
0.
Okay. C?
0.
And D?
1.
Okay. Now, let us try and find. So this del phi del t we will call the temporal derivative. It is, suppose phi is temperature, and you keep a thermocouple in a flow field at a particular point and record the temperature with time. Small t is the time. Okay. So from your time temperature record, using numerical differentiation, you can find the rate at which temperature is changing with time at that given point. And that will be the meaning of your del phi del t. You can either call it an Eulerian derivative or temporal derivative. It is the rate of change at a given point in space. And del x del t is 0 because the point in space does not move. So the x coordinate of a point does not move. So del x del t is 0. Okay. Now, of course, if you want to do it mathematically, then look at the definition here. Del x del t. All right. So if I say phi is x, then phi x y z t is x, and phi x y z t plus delta t is also x. So in the numerator here you have x minus x, which is 0 for all delta t. So del phi del t is 0 because there is no time dependence over there. But now if I ask you to find d phi dt, this means the rate of change of phi for a particle. So if I look again at same four questions, what is d phi dt when phi is x? Okay, it means a different thing. So 1a means I'm asking you what is the time rate of change of the x coordinate of a particle.
Velocity in the x direction.
So you expect it to be the velocity. Okay. So this would be the x component of velocity, b would be the y component of velocity, c would be the z component of velocity. What about the last one?
1.
That's what you expect. Now let us see whether this expression is giving you this expression. Okay, is giving you the same thing. What do you expect? So we want dx dt, which is del x del t plus vx del x del x plus vy del x del y plus vz del x del z. Now why are we looking at all this? Because we'll be doing similar. So I thought let us first start from simple things which you already know and then move on to more complex things. All right. So there are two time derivatives in the equation at the top of the screen. On the left hand side is the total derivative, okay, or the material derivative or the substantial derivative. It is a derivative following the fluid particle. So physical meaning is the time rate of change of the x coordinate of a particle. And the first term on the right hand side here is the left hand side you can also call the Lagrangian time derivative, because Lagrangian approach means you're following the particle. On the right hand side here, the first term you can call the Eulerian time derivative or the temporal derivative. So this is the rate of change of x at a given position. So that point is fixed. The particle which was there at time t moves to a different point or position, and the same old position is occupied by another particle. Okay. So when you look at del x del t, you're looking at the change in x for different particles which are occupying that point, same point. Okay. But since the point is not moving, we expect this to be 0. Whereas the derivative on the left here is the rate of change for a particle. The particle moves from one point to another point. So it is at a given position at time t, it will be at a different position at time t plus delta t. Alright, so we need to know what is all these partial derivatives: del x del t, del x del x, del x del y, and del x del z. Okay.
Hello, sir.
Yeah.
Sir, so if the coordinate frame moves with some velocity vx, then that del x partial derivative of x with respect to t will not be equal to 0.
Partial derivative of x with respect to t will not be 0. But see,
sir, in the temporal term, the derivative, like the point we are considering, does not move with respect to time, right? Like it will be fixed in space.
Right.
So that is when the coordinate frame is fixed, like it is not moving with respect to another point. So if the coordinate system is also moving, if the x is also a function of time, then what will happen? So if del x by del t is always equal to 0.
Yeah. So right now I have not looked at the Galilean transformation yet. This is a stationary coordinate system.
Okay.
Okay. So I'm reviewing the concept of material derivatives. Then I'll move on to Galilean transformation.
So in Galilean transformation, like in that coordinate system, that del x del t term will not be equal to 0.
It depends on which coordinate. There will be two coordinate systems there. Okay. So there will be several partial derivatives. There will be a partial derivative with respect to t, another with this where x, y, z is kept fixed. There will be another partial derivative where x prime, y prime, z prime are kept fixed. Okay. So I'll come to that later. Okay. But you see here, if you look at what are kept fixed, you see del x del t means del x del t keeping x, y, z constant. So if x is constant, the derivative is 0. Okay. And here if you look at del x, y, z and t are kept fixed, but x is changing. So this is 1. And if you look at del x del y here, you see what is kept fixed is x, z and t. So if x is kept fixed, that means x is a constant here. Okay, so it is 0. And similarly, del x del z is a partial derivative keeping x, y, and t kept fixed. So if x is kept fixed over here, then in the numerator here, this is also kept fixed. Okay, so you have already given me the answer, but I went through it again. Del x del t is 0. We are looking at a coordinate system which is fixed, it's not moving. Del x is 1, del x del y is 0, del x del z is 0. So it's easy to see why the last two are 0, because x and y are independent coordinates. So if x is independent of y, that means even y is changing, it's not affecting x. Similarly, x is independent of z, so a change of z does not affect x. It can remain a constant, so it is 0. But if x is changing, then del x must be 1. And these are, of course, we can also look at it from the definition here. Alright, suppose I say phi is x, look at del phi del x, or del x del y. Alright, so numerator, this term is x, and this term is also x, so difference is 0. Similarly, for del phi del z, if phi is x, this term is 0, this term is x, and this term is x. So the difference is 0, as in the first case. Alright, but if you look at del x, then this term is x plus delta x. Okay, and this is You're subtracting x from x plus delta x. So x cancels out and you get delta x divided by delta x, which is 1. So these are obvious, but the reason I'm going through all this is to emphasize certain things. The meaning of the partial derivatives. Now, if you want the material derivative, let us see what this expression, does it give you the right answer? Well, del x del t you're saying is 0. Then to that you add Vx multiplied by del x, which is Vx times 1. Okay. Then to that you add Vy times del x del y, but del x del y is 0, so it is Vy times 0. And the last term is Vz del x del z, so it is Vz multiplied by 0. So the last two terms are 0, the first term is 0, and the middle term here, the second term is Vx. So as you might have expected, dx dt is Vx. So to emphasize this, I've written it in words. The temporal derivative or the Eulerian derivative, del x del t, represents the time rate of change of the x coordinate of a point, which is fixed. So this partial derivative is 0 as the x coordinate of a point is constant, independent of time, since the point does not move. Now, the material derivative dx dt, or the Lagrangian time derivative, represents the time rate of change of the x coordinate of a particle. And this total derivative is the x component of the velocity of the particle. Now, likewise, you can look at partial derivatives of y. Only del y will be 1, the other 3 will be 0. And the material derivative of y will be Vy. So for the sake of completeness, I've written all this, but you simply replace x by y and you get everything in this slide. Likewise, now you can look at partial derivatives of z. Now again, some of these partial derivatives will be required when you look at the Galilean transformation. That's why I'm going through it. Okay. So del z will be 1 and the other 3 partial derivatives will be 0. Why? Because z is kept fixed. So if you look at del z del t, you have a z over here. Okay. If you look at del z del x, you have a z over here, which is kept fixed. And if you look at del z del y, you have a z over here, kept fixed. But if you look at del z, there's no z here. What you have here is x, y, and t. And once again, the material derivative of z will be Vz. Now, as a homework, you can show that phi times d phi dt is d dt of phi square by 2. So this is like any derivative. The way to show it is start with the definition. Okay, and look at what is phi del t, what is phi del x, what is phi del y, what is phi del z, and then substitute over here. And as a second exercise, you can look at the scalar product v dot dv dt. So if you want to find a mechanical energy balance, okay, then you may need to take the scalar product of the vector momentum equation with v. Then on the left hand side of the equation, you will come up with a term which is v dot dv dt. And you can show that this is d dt of v dot v by 2. Alright, now any questions regarding this material? If not, then I'll stop sharing this and open another document. Is the new document visible?
Yes, sir.
Yes, sir.
Okay. Now we have to make use of this concept of what is called the kinematic boundary condition at the surface of an impermeable solid wall. So this will help us find the direction of the velocity of an inviscid fluid flowing over a solid wall. And this we need for making all the predictions, whether it's for the turbine or for a centrifugal pump. Okay. Now, if you look at a book on fluid mechanics, they'll not give detailed explanations. The final result will be there. So what I'm trying to do is review all these concepts so that once these fundamentals are clear to you, you can quickly read and understand the material relating to the prediction of the performance of turbo machines. Now consider a point which I will call capital P on a stationary solid surface, which is immersed in a fluid, so the fluid is flowing over the surface. Okay. Now, I've used the term stationary over here because later on we look at moving surfaces. So in pumps and turbines, you will have vanes or blades which will be moving. Okay. But first we need to look at the kinematic boundary condition for stationary solid surface. The surface may be a plane surface or it could be a curved surface. So let n be the unit vector normal to the solid surface at the point P. So in my notation, if you see a bold-face quantity here, then you have to understand that this refers to a vector quantity. Now I have drawn some figures where I've written here, for example, V here, my hand. So either I have to put an arrow on top or a bar on top. So I prefer a bar over here. Okay. So this figure shows a porous solid adjacent to a fluid. So on the left you have a solid, but it's not an impermeable solid. So I have shown these dashes and gaps in between to indicate that fluid can flow through this. So these are the holes or the pores on the surface. So this dashed line is the interface between the solid and the fluid. And I'm considering a point P over here, and n is the normal. So n hat, this sign means a unit vector. So magnitude is 1, it shows the direction. Now, suppose you have a plane surface, then I can move from this point to another point and the direction of n will remain unchanged. But if it's a curved surface, the magnitude will remain 1, but the vector will point in different directions. So you have a local n at each and every point which may be different. Now consider a small area dA over here. Okay. Infinitesimally small area dA surrounding the point P. Now what will be the rate at which fluid crosses this surface dA in, say, meter cube per second? So I've used the symbol Q with a subscript flow for volume flow rate. The reason being that sometimes in this particular course you may use Q for heat and Q dot for rate of heat flow. Okay. So this flow means is fluid flow. Okay. And if you don't have a subscript, it means just heat. So dQ flow, you know, is the normal component of the velocity, which I may call Vn multiplied by dA. So if you know the vector V, I can resolve it into a component normal to the surface and a component tangential to the surface. So I'm using the subscript V subscript n to denote the normal component of the velocity, and V subscript t to denote the tangential component of velocity, that is the component of the fluid velocity which is tangent to the surface. Okay, sometimes this could be 0. Okay, if it's a viscous fluid. But even if the viscous fluid is a porous wall, it may be at some small number. Okay. But whatever it is, if it's a porous solid, fluid can seep through the solid, through the pores. So normal component of velocity can be non-zero. Now in terms of the vector V, this Vn you can think of as V. If I say the angle between n and V is some theta, it will be V cos theta. So that is the same as V dot n, because if you look at V dot n, it is the magnitude of V into the magnitude of n, which is 1 times cos of theta. So V dot n is V into 1 into cos theta, where theta is the angle between this angle between n and V. So we can simply write the dq volume fluid through this infinitesimal area over here, this small area, as V dot n dA. So Vn or V dot n, the units will be meter per second, and dA is meter squared in SI units. So meter per second into meter square will give you meter cube per second. So here I've used the vector V to denote the fluid velocity at the point P. Now since later on we'll be looking at moving frames, I've written in brackets absolute velocity, but if nothing is written, then you have to understand, it is understood that this is the velocity with reference to a frame of reference which is stationary. Now suppose the solid is an impermeable solid, then the volume fluid through an area element surrounding any point on the surface is 0. So if that is the case, then the normal velocity component, which I have shown here for a porous solid here, this magnitude will be 0. That means the velocity vector will be then tangent to the surface if it's an inviscid flow. So dq flows 0 at any point means that V dot n is 0 at any point on the surface. And I have written these keywords in bold. This holds for the impermeable solids and of course stationary also. Now if you look at a book, they may not talk about stationary because that book may not talk about moving surfaces at all. Okay. So since we'll be dealing with moving surfaces, I have emphasized all the keywords: impermeable, stationary, and solid surface. The normal component of the velocity is 0. So this condition is often referred to as the kinematic boundary condition. It is also called the no penetration boundary condition at the surface of a stationary impermeable solid surface. So I've drawn another figure over here. Now, so this is the interface between the fluid on the right and the solid on the left. And now I'm taking a case where the solid is impermeable. The fluid cannot seep through the surface. Now if I consider point N and point P here, and the normal to the surface at this point is n hat. Alright. So this caret sign or hat sign indicates it's a unit vector. And I've drawn the tangent to the surface here. Then if the fluid is inviscid, the direction will be normal to this, so that n dot V is 0. So n dot V will be 1 into the magnitude of V into cos of the angle between them. So the angle between n and V must be 90, so that cos 90 is 0. Okay. Now if it's a viscous fluid, then the magnitude of V is 0. So we cannot talk about direction at all. But as we are saying, if we consider the fluid to be a viscous fluid, you have to use the techniques of to summarize, we have considered two cases: a porous solid adjacent to a fluid, that is in the first figure, and the second figure we have looked at an impermeable solid adjacent to a fluid. Okay, and we are considering a particular point on the solid fluid interface, and we have drawn the orientation of the surface at that point by indicating it by the unit normal, which is pointing from the solid into the fluid. So if it's an inviscid fluid, if I ask you what is the direction of the velocity vector at this point, it may be in any arbitrary direction. We don't know what that exact direction is because it can have a normal component as well as a tangential component. Since the fluid can slip, the tangential velocity component will be non-zero. And if it's porous, there may be mass transfer through the pores. So there will be a normal component also. So unless you know what is the magnitude of Vn and the magnitude of Vt, you cannot predict what is the direction of velocity vector. But now, if you look at an impermeable solid, whether it's viscous or inviscid, it does not matter. There will be no mass transfer across the solid surface. So the normal component of the velocity will be zero. Okay. So this Vn here will be zero, which means that if it's an inviscid fluid, we can predict what is the direction of the velocity. The velocity vector will be tangent to the surface. We may not be able to find out easily right now what is the magnitude of the velocity, but we can say what is the direction of the fluid flow. If you model the fluid as being an inviscid fluid. So this is an important concept that we'll be using. Now, of course, as we have said before, if the solid surface is porous, then V dot n is not zero. Now consider the flow of an inviscid fluid. And I've written in parenthesis the meaning of an inviscid fluid. Inviscid means the viscosity is zero. And we are considering an inviscid fluid flow over a solid surface which is stationary and impermeable. Now we know that if you have a real fluid which satisfies the continuum hypothesis, then the real continuum fluid will stick to a solid surface, and it sticks to a solid surface because of its viscosity. So a viscous continuum fluid satisfies what is called the no-slip boundary condition at the surface of a stationary solid. That is, the tangential component of velocity is zero. Now if you want to be more elegant, you can say n cross v is zero, where n is the normal. So n cross v will be a vector which is normal to n. Okay, so it will give you the component of the fluid velocity which is tangent to the surface. Now, of course, for simplicity here, I've just shown a two-dimensional case. Okay, but in a three-dimensional flow, you will have two tangent directions. There will be two. You can have a tangent plane, and if you want to describe a vector in the tangent plane, you will need two basis vectors. So you have to have two tangent vectors in the tangent plane and one normal vector. But if you take n cross v, it will give you a vector which is lying in the plane which is normal to n. So if you want to generalize, then you will have Vt1 equal to 0 and Vt2 equal to 0 for a 3D case. But n cross v equal to 0, if you say it is a vector equation, this takes care of both the tangential component of velocity. But anyway, the thrust of this course is not for this no-slip condition. This I have included so that you understand what is the difference between a viscous fluid flow and inviscid fluid flow. And some of you may be taking the course on advanced fluid mechanics this semester. It is a core course for dual degree students of thermal and elective for BTech students. Okay, so there you will be studying viscous fluid flow in more detail. So just so that you don't get confused, I have included this part to contrast this with the case of an inviscid fluid flow. So in this course, we're taking a model of fluid flow which you can say is constant density and zero viscosity fluid flow or ideal fluid flow. So why have we done all this? Because we want to predict what is the direction of the velocity vector at an impermeable solid surface. Okay. Now, of course, this question is pertinent only when the fluid is an inviscid fluid. Because if the solid surface is stationary and the fluid satisfies the continuum hypothesis, the velocity vector itself is a zero vector at the solid surface. So this question is meaningless. Okay. So we are looking at what we call the inviscid model, and I've shown these two figures before here earlier, but I've shown it here again. And I have a third surface here, and a third figure here, which is the curved surface like this. Okay, and you have fluid on the above and an impermeable solid below, and the interface between the solid and the fluid is a curved surface. So I've shown 1, 2, and 3 points. And at each of these points, I have indicated the unit vector normal to the solid fluid interface, which is pointing from the solid into the fluid in all 3 cases. So this I've called N1 with a hat or caret sign on top. This is N2 with a hat or caret sign on top, and this is N3 with a hat or caret sign over here. So N1 is a unit vector, magnitude is 1. N2 is a unit vector, but these two are not parallel vectors. So N2 is not the same as N1. It is pointing in a different direction. And again, N3 is another vector. Magnitude is the same. This figure may not be to scale. I've drawn it in a hurry. Now, suppose I say the fluid is an inviscid fluid. Then it will slip along the wall. Okay. And at each of these points 1, 2, and 3, I have indicated the direction of the velocity vector. Of course, I have assumed here that the fluid is flowing from left to right. Okay. So the arrow here, arrowhead, indicates the direction of the flow. So this velocity vector is tangent to the surface at 1. V2 is a vector which is tangent to the surface at 2. So the bar means here a vector quantity, which is not a unit vector. And V3 here is a vector which is tangent to the surface over here. Now for the dot product to be 0, since n is a unit vector and v is not a 0 vector, it has some magnitude. The dot product can be 0 or the scalar product can be 0 only when the angle between the two vectors, that is n and v, is 90. So the angle between n1 and v1 in this case is 90. The angle between n2 and v2 is 90, and the angle between n3 and v3 is 90. Okay. So one of the advantages, as you can see, of modeling the fluid as an inviscid flow is that if you have a impermeable solid surface, then if it's stationary, you know what is the direction of the velocity vectors along the surface. And if you want to apply Reynolds transport theorem and rate the force on the surface, etc., you will need to find momentum fluxes. So you need to know the direction of the velocity vectors. But of course, this is just a geometric interpretation. It is not giving you the magnitude of the velocities. To quantify the magnitude, you have to look at some equations. Okay. Now I guess I put an arrow over here. So this hashed surface is a interface between the impermeable solid and the fluid. Since the normal component of the velocity is 0 and the velocity is tangent to the surface, this surface is what you will call a stream surface, which consists of streamlines. So the vector v, representing the velocity of an inviscid fluid, this is the keyword, at the surface of a stationary impermeable solid surface. So there are two keywords. One is stationary, other is impermeable, and of course it's a solid surface. Is that it is tangential to the surface. All right, now let us generalize this and consider. All right, before that, any queries? So this idea of talking about the kinematic boundary condition in the context of this course is that if you model the fluid as an inviscid fluid, then you know what is the direction of the velocity vector. So if you consider the fluid particle which is sitting on the wall, It is moving, it is slipping along the wall. What is the direction of the velocity vector? That will be required later on in the analysis. Now consider a point P on a moving solid surface, which is immersed in a flowing fluid. So fluid is also moving and the solid is also moving, let us say. So let capital U vector be the velocity of the moving solid at the point P. Now if the moving solid is translating, then the velocity at each and every point on the solid will be the same. But if the solid is translating as well as rotating or simply rotating over some point, then this vector U in direction and magnitude may be different at different points. So what we are trying to do is generalize the analysis which we have already done to the case when the surface is moving. Now let W vector be the velocity of the fluid relative to the moving solid and again at the point P. So if V is the absolute fluid velocity, okay. So all these velocities are with reference to a stationary frame of reference, okay. So V by definition, so this equal to sign with the triangle means defined. V is V. I have used the subscript REL for relative velocity. It is the absolute velocity of the fluid minus the velocity of the solid. Now, writing subscripts and superscripts makes the notation cumbersome. So, we'll use a subscript-free notation which I'll call W vector. Okay. So, I'm using V for the absolute velocity, W for the relative velocity, and capital U for the velocity of the solid. So, if I want the velocity of the fluid relative to the moving solid, I have to subtract the velocity of the solid from the velocity of the fluid, and I get the relative velocity. Now, again, to emphasize the difference between translating and rotating bodies, okay, if the solid is translating, then this U is a vector which is the same at each and every point. If the body is accelerating, U can depend on time but not on space. But if the body is moving with a constant velocity, then U will be a constant. So for the timing, in the case of the Pelton turbine, we'll be using linear momentum analysis. So we'll assume that U is a constant. Okay, so as before, let N be the unit vector normal to the solid surface. And consider an infinitesimally small area element around P. So what is the volume flow rate? Now, through an area element of the moving surface. If the surface is moving, then you have to take the normal component of the relative velocity. So it is going to be W dot N dA or V rel dot N dA, where V superscript REL is the fluid velocity relative to the moving solid at the point P. Or you can say W subscript N is the component of the relative velocity normal to the surface. So this N subscript indicates it's the normal. Okay. And Wn here is W dot N. So if you look at the magnitude of Wn and magnitude of W dot N, they are the same because N is a unit vector. So if the solid surface is impermeable, then the volume flow rate will be 0, which means that now W dot N will be 0 or V minus U, capital U dot N must be 0. So you can refer to this equation as the kinematic boundary condition or the no penetration boundary condition at the surface of a moving impermeable solid surface. So now there are three keywords here. Solid here is still impermeable, but now it is moving, not stationary. Now if it's stationary, then U will be 0 and W dot N will be V dot N. So this condition will reduce to the previous condition when the surface is stationary. So this is more general. You can view this as a generalization. So now if we define the vector W to be V minus U, which represents the velocity of an inviscid fluid relative to an impermeable solid surface which is moving with the velocity u, then W vector will be tangent to the solid surface. Okay. So now we can predict not the direction of V, but the direction of W. So how to find the vector V at the surface? Well, simply use this definition. W is V minus U, so V will be W plus U. Okay. So if you do this vector addition, then you can find what is V. And if you represent this by a vector triangle, then this is called a velocity triangle. Now let us see why we are doing all this. So let us look again at the model of a Pelton turbine, which is a symmetric curved bucket which is translating in the x direction. So here you have a nozzle here which is directing a jet of water. You have air above, air below. So this blue line is the interface between the air and the water. Vj is the jet velocity relative to this fixed coordinate system xy. So this jet will strike the bucket provided the speed of the translating speed of the bucket is less than Vj. Okay. So if I say W is the relative velocity here, if I draw the control volume like this and say this is section 1, the direction of W1 is known because you know the direction of the jet. And the magnitude of W1 will be Vj minus U. Okay. Now, the fluid particles will move in a curved streamline here because this curved surface of the bucket, okay, is a stream surface, so it is a streamline. Okay. And you can draw another streamline in between over here. Okay. So at the exit over here, there are two exits, which are called section 2 and section 3. The direction of the velocity, relative velocity, will be tangent to the surface. Okay. So this direction is known. The magnitude will have to be found from some analysis. Okay. And the velocity of translation of this bucket is known. So here in this figure, I have used O prime, X prime, Z prime as a coordinate system attached to the moving bucket, such that O prime X prime is parallel to X and O prime Y prime is parallel to OY. But the origin O prime here, this is moving to the right with vector velocity U. So to V2, if I add U, I'll get W2. Okay. So the direction of W2 will depend on the magnitude and direction of course, for a given bucket, the direction of W2 is fixed. Okay. But the magnitude will depend on what is U and what is Vj. We'll come to it later. And so you have a parameter which is Vj, the speed of the jet, and you have another parameter here which is the speed of the translating bucket. So depending on that, the angle between W2 and V2 can change. Right? So I've drawn it here in a hurry. This is not a 90-degree angle. Okay. Similarly, if you look at the other outlet here, the relative velocity, which I'm calling W, and I put a subscript 3 here, this will be parallel to the tangent to the bucket at this point, exit. Okay. So to W3, if I add U, we get V3. Now since here the bucket is translating, your U3 and U2 is the same. So I have not put any subscript here. But when we look at the centrifugal pump, you see the blades mounted on a rotor which will rotate. And you see that U will depend on the radius, the radial location. So now if I look at this, if I say this is the x direction, here in this figure, V3 has a positive x component as a positive y component. Okay. Now, if the magnitude of U is less, this V3 instead of pointing towards the right, it can point towards the left. So the x component of V3 could be negative. But so at section 3, the y component of V3 will be positive. It will be in the positive y direction. But the x component can be either in the positive x direction or the negative x direction, or it could be parallel to the y axis. That is, the x component could even be 0. So this is, I'm talking about the absolute velocity. And if you look at section 3 here, the y component of the absolute velocity, that is always going to be negative. But the x component could be either positive, it could be negative, or it could be 0. That is, the absolute velocity could be in the negative y direction. So it is not only the geometry of the bucket. So this angle beta 2 here and this angle beta 3, these are called the blade angles. So usually the bucket is symmetric and beta 2 will be equal to beta 3. But I've shown a general case over here. So I'm calling this angle beta 2, this vector W2, and this V2. So this is an example of what I'm calling the velocity triangle. And this is another velocity triangle. So once you get familiar with the concept of velocity triangle, and you know which of the vectors is going to be tangent to the surface, the rest is easy. So the kinematic boundary condition, if I go back to it, this equation, I can write as v dot n minus u dot n equal to 0. Or I can say that v dot n is u dot n. So the normal component of the fluid velocity and the normal component of the solid velocity, they will be the same. That is another way of stating this. So by spending this time now, I think I've clarified a very important concept: how to find the direction of the relative velocity vector when the surface is moving. Okay. Unfortunately, this is not explained in this way in any book. Okay. What you have to understand is that you're modeling it as an inviscid flow. Okay. Because if it's a viscous flow, then the velocity at the surface will be 0. Okay. And later on, we'll assume that across the section V2, the velocity vector W2 and the V2, they don't change. So at each and every point, it will be the same. So that's a one-dimensional approximation. But to begin with, you have to know what is the direction of the velocity vector. Any questions? All right. Then I stop. If you have any questions.
Sir.
Yeah.
Can you share the documents?
Yeah, I can hear you.
Thank you.
Do you have a question?
Sir, when will you share the slides or the documents?
Hello. Any questions?
Yes, sir. When will you be sharing the documents which you used today and before?
Okay. Now, should I send it by ERP mail?
Yes, sir. Anything would be fine.
Okay.
Sir, you can also share it on Teams, Microsoft Teams.
MS Teams.
Yes, sir. There is a file portion, file segment, the tab.
Okay. Okay. All right. So we'll meet again at 2 o'clock. Okay. Maybe this afternoon I'll share the files. Okay.
Okay. Thank you, sir.
So I'll hang up now. It's already 12.